A central idea in geometric group theory is to look at groups, or in general metric spaces, from very far away. So more generally, this is the idea of coarse geometry, or it's looking at metric spaces from so far away that we are looking at only their asymptotic properties. Ignore all fine structure. Incidentally, this means we are ignoring continuity as well. Yeah. So let's just recall some very basic things just for comparison or precision. So suppose x and y are metric spaces. Okay. Then of course an isometry. First let's look at what's an isometric embedding. An isometric embedding is a map f from x to y such that distance between f of x1 and f of x2 is the same as the distance between x1 x2 for all x1 x2 in x. These are of course familiar notions. And what is an isometry? Well, isometry is from x to y, which is first of all it's isometric embedding, and it's also onto. So a remark here is that one-to-one is automatic, and continuity or isometry of inverse is also automatic. Okay. So an isometry is just a map which is an isometric embedding, and it's also onto. So this is enough, and we can define the inverse. So f inverse of y is unique x such that f of x equals y. Now what we want to do is look at coarse versions of this. That's why these rather simple familiar notions I looked at with a little care. Okay, so what we'll look at are coarse versions. So coarse versions, as I said, is look from very far away. We are looking at scales of only light years, so anything that happens on the scale of meters is to be ignored. That is, normal human scales is to be ignored. So again, x and y are metric spaces. X, y are your usual metric spaces. We'll generally assume them to be complete. Okay, it may not be formally necessary, but there's no good reason to not assume them to be complete. As I said, we rarely assume them to be compact because from very far away a compact space looks like a point. Okay, so definition, f from x to y is a KC quasi-isometric embedding. If so, this is a coarse version, but it depends on certain constants. If well, for all x1 x2 in x, what happens is the distance between f1 of x f of x1 and f of x2 well, now instead of being equal to the distance between x1 and x2 is sandwiched between the distance between x1 and x2, allowing a scale, but then we also allow something else, which is we allow an additive constant. Okay, so any bounded number is taken as small because this is all supposed to be viewed from a very, very large scale. So given any c, so what we need is the distance is less than or equal to this, but of course we want a bound in the other direction also, so that will naturally be 1 over k times distance between x1 and x2 minus c. Of course the left hand side may be negative, that's not a problem, we are just lower bounding by a negative number. Yeah. And a quasi-isometry, f from x to y is a KC quasi-isometry if f is a quasi-isometric embedding with the same constants k and c. Incidentally, often we drop the constants as usual, kc, quasi-isometry, and just say it's quasi-isometric. That means there is some kc for which it's a quasi-isometry. And then we would like to say onto, but we are looking from very, very far away. So when we look from very far away, it doesn't mean that we can't see the difference between 2 points that are very close to each other. In fact, with say distance less than c. So what we need is just that y, instead of y equals f of x, which would be onto, we take the c neighborhood. So this is c neighborhood. So it's almost onto. Okay, so a couple of remarks here in this philosophy. So this is the natural relation that we want to take on spaces when we are viewing them from far away. A couple of remarks here. This part is called coarse lipschitz. Okay, so another view of quasi-isometries, which I will just sketch because it's a sort of more conceptually nice view. This is maybe more convenient in practice, so I've taken this as a definition. I won't prove anything here. Another view is that we have coarse Lipschitz maps. As I said, this is f from x to y. There exists k comma c such that distance between f of x1 and f of x2 is less than or equal to k times distance between x1 and x2 plus c. Now if I didn't have c, if c were 0, this would just be Lipschitz. Okay, so just this part of it is just Lipschitz. And the natural relation on metric spaces is really by Lipschitz rather than isometric. So this is just the Lipschitz condition. So this is the coarse Lipschitz condition where we add a c term. But to actually get a notion, when we are looking from far away, we not only need to coarsen the Lipschitz, we need to coarsen an equivalent of notion of being equal. Okay, this frequently happens. In algebraic topology, we look at equality as being homotopic, for example. So this is saying that f comma g from x to y. So if I have f from, we say f is equivalent to g if there is some c greater than 0 such that for all x in x, distance between f of x. So I call this an exercise. X and y are quasi-isometric if there exists f mapping x to y, g mapping y to x, both of which are coarse Lipschitz, and f composed with g is equivalent to identity. These are different identities. Of course, g composed with f is identity. Well, this will be the identity on y, this will be the identity on x. Okay. So quasi-isometry really becomes isomorphism for a given class of maps and for a given notion of equality. Okay, just like homotopy, equivalence, or anything else. And we always want to view things in this way to put it in a nice mathematical framework. But for our purposes, this is a digression and an exercise. Yeah, I should emphasize exercise. Not a difficult exercise, but an interesting one in the sense of interesting in terms of what you learn from it. But now let's return to our older definition and take a simple example. So this seems almost silly. So z subset of x, and suppose this is quasi-isometrically embedded. Sorry, isometrically embedded. Well, this simply means that is restriction metric. So the metric on z comes from restriction of the metric on x. Okay. Then what happens if there exists c such that nc of z equals x? Then the inclusion map, in fact, inclusion function, let's say, is a quasi-isometry. Okay. So what happens in this case? Inclusion map is a quasi-isometry. This seems almost silly that I've even weakened it. All you needed was Z to be quasi-isometrically embedded, but isometrically embedded means that. But the reason for considering this simple point is that if you take G with the word metric ds, well, this we have seen includes in the Cayley graph of G with the generating set S. This is a quasi-isometry. Okay, and so now I'll make a very important remark here. This is that quasi-isometries, the inverse, we'll talk about the inverse in a moment, is not continuous. You see, the left hand side is a discrete topological space, something like this, and this guy is a graph. It's connected. Okay, it's a graph and it's connected. So if I had any continuous function here, it would be constant. And a constant has no chance of being a quasi-isometry other than if the spaces have bounded diameter, which these don't in general. So quasi-isometries, as I said, and when you're looking at things coarse, we don't respect continuity. Okay, so let me just make a comment here about inverses. Inverse of quasi-isometries. What can we say about the inverse? So suppose f from x to y, just spaces x to y, is a KC quasi-isometry. Okay, then I want an inverse function from this. So question here. So I defined a quasi-isometry, and I would say x is quasi-isometric to y if there is a quasi-isometry. But is there a quasi-isometry in the other direction? Well, so you define g from y to x such that something holds, and this is very, very far from canonical for y in y. Okay, so let's see how we'll define it. We'll define it this way. For y in y, there exists x in x such that y belongs to neighborhood C of f of x. Okay, well, then you define g of y, g of y equals x for some such x. Okay, so pick an x for this and define g of y equals x. Well, this looks like a terrible function, and indeed it is often not continuous, as I already said, but you can make it much, measurable. For example, if you want it, it need not be so bad. Let me just draw a picture as an example. If I had a lattice like this, okay, or a discrete set, somewhat irregular lattice, well, then what I can do is that so in this case the lattice itself is x and the complete ambient space is y, and I want a map from G to y, and so long as the lattice is sort of almost dense, that is a neighborhood of that is everywhere in y, you can do this. And what you do is you take a region around each point and map it to that point, and something which is just outside this region has perhaps gone the other way to another point. Maybe this guy went here. Okay, so these dots, remember, constitute x. So we have a map. This is not continuous, but it sort of tears up the space. So what can we say about this? That I'll leave as an exercise. Exercise here is G is a quasi-isometry. Not necessarily with the same constants. So part of the exercise is to find what the constants work. Okay, so this guy, so if I have, in this case this was an inclusion map and an isometry, but in general if I have a KC quasi-isometry, just choose an inverse in a sort of arbitrary way. Okay, remember in metric spaces this construction becomes canonical where C is 0, that is you pick an inverse, and this is automatically an isometry. and it's a good exercise to do. Okay, so finally we'll turn to the situation that we were left with in the last screencast, which is different generating sets. You see, our problem with associating Cayley graphs or groups or word metrics to a group was the following: that if I take a G, a group, okay, and then say S prime are generating sets, okay, then we had two constructions. First of all, the word metric and the Cayley graph, which had their respective advantages, but more seriously, for different generating sets we got different metric spaces. Okay, so we have already seen that the word metric and the Cayley graph are quasi-isometric. Okay. In fact, K could be taken as 1 in that case, since we have an isometry. But in fact here, I should emphasize finite generating sets. I assume the group is finitely generated and I've taken two finite generating sets. Otherwise this is very easily false. So G comma ds is quasi-isometric to G with respect to S prime. Okay, so let me sketch the proof. I'll point out the main step in the proof. The main step, where do we use finiteness? Okay, so we look at the set of all generators S in S and look at their S prime norms. Okay, norm with respect to the other set. What do we know about the norm with respect to the other set? We don't know much actually. For example, it could be very long, but we know these are finitely many numbers. Okay, so if I take their maximum, this is still a finite number. This is a finite number, in fact an integer the way we have set up, but finite real matters. Okay, so what does this mean? So this means that S in S implies that norm of S prime is less than or equal to K. But recall that norm S with respect to S is equal to 1. So for generators, at least, when the norm is 1, the S norm is 1, the S prime norm is at most K. So you can guess from this that we are scaling up by K. So for G in G, norm S prime of not S but G is less than or equal to K times its norm with respect to S. This is what I'll prove and leave the rest as an exercise. So suppose norm G equals N, then what do we know? G is going to be S1 to the epsilon 1, Sn to the epsilon n, Si in S. So now we have our triangle inequality, or rather that property B or something of the norm. So norm G S prime, well, it's less than or equal to norm S1 S prime. Now I dropped epsilon I because of the symmetry property of the norm, plus Sn norm Sn of S prime. Now each of these is less than or equal to K, so this is less than or equal to K times N, which is K times norm G. Okay, so this concludes the proof of the lemma. Well, we can also do it in the other direction, okay, and find another constant and take the bigger of the two, as we usually do. You can find K prime so that reverse inequality is true, and using these you can pass from norms to distances and complete the proof. So this is the key idea. The point I wanted to emphasize is the finiteness is used simply by taking norm over a finite set, and that contains all the information. Okay,